Hello my dear children, once again welcome to our physics class. Hope you all are fine over there. Children, we are discussing chapter 7 alternating current, and in the previous session we had discussed about LC oscillations, LCR circuit, resonance in LCR circuit. Today we are going to discuss a new concept of this chapter, that is transformers. So two types of transformers are the step down and step up transformer, and these transformers are used for long distance power transmission. So today let's discuss about the principal, construction and working of transformer. Let's get started with today's session, my dear children. Let's continue with our chapter 7, alternating current. So today we are going to discuss about transformers. What is a transformer? A transformer is a device that changes voltage from one value to another. That means if we want to increase the voltage or if we want to decrease the voltage, we can use transformers. Power at the input end is equal to power at the output end. Only the voltage will increase or decrease. So there won't be any change to the power both at the input and the output end of a transformer. If the input power is 10 watt, then the output power also will be 10 watt. So keeping the power constant, only the voltage will increase or decrease. Okay, so that is the peculiarity of a transformer. Let's discuss about the principle of the transformers. Transformers work on the principle of mutual induction, and you had already studied about mutual induction. So suppose there are two inductors, and if some current flows through coil 1, there will be change in current. As a result, there will be change in magnetic flux, due to which there will be a change in magnetic flux in the coil 2, and because of which EMF is induced in the coil 2. Okay, that is mutual injection. That is what is called mutual induction. So if we have two coils like this, let this be our one coil and let this be our second coil, and this coil is connected to an AC source. So let this be our coil 1, let this be our coil 2, and when the coil 1 is switched on, current starts to flow through the coil 1, and that will be an AC current, and AC current changes its magnitude every time. So the flux associated with the coil 1 changes. Since coil 2 is very close to coil 1, any change in the magnetic flux associated with the coil 1 will be reflected in coil 2 also. So the magnetic flux associated with the coil 2 also now change, and due to which an EMF is induced in the coil 2. So whenever there is a change in magnetic flux, an EMF is induced, and here in the coil 1 the EMF induced will be self-induced EMF, because the flux changes due to the EMF is induced due to the change in magnetic flux associated with the same coil. But in coil 2, EMF is induced due to the change in magnetic flux associated with the neighboring coil, that means this coil. Okay, so coil 2 undergoes mutual induction and coil 1 undergoes self-induction, and the principle of transformer is mutual induction, and that is what is written here in this para. Okay. Now construction. Construction means let's be familiar with the important parts of a transformer. So a transformer consists of a primary coil and a secondary coil. Okay, so this is the structure of a transformer. This is the core of the transformer, and a primary coil is there. So let this be our primary coil and this be the secondary coil. Okay, so primary coil has n number of turns of wire over a piece of soft iron core. So this is the soft iron core. This is our soft iron core, and the coils are wound over this soft iron core. So this is the primary coil, and it has n number of turns over a piece of soft iron core, and it is the input end. So primary coil is the input end of the transformer. And this will be the secondary coil. Okay, the secondary coil also has a specific number of turns and n number of turns, and it is the output end of the coil. We receive output from this end of the transformer. Okay. Next, soft iron core. The soft iron core, the hysteresis curve for iron is extremely thin, because of which it covers minimum possible area. And you had not studied about the hysteresis, so let's not discuss more about the hysteresis phenomena and all those things, because it has been deleted from your syllabus. So, soft iron core is used in the core of the transformer, and the coils are wound over the one side and the second side of the soft iron core. So what are the important parts of a transformer? Primary coil, secondary coil, and a soft iron core. And this is the figure of a transformer. So this part of the soft iron core is the primary coil, and the current flowing through this coil can be considered as primary current. This is the input end, and the voltage is the input voltage. Okay, and this end, that means the blue color coil, represent the secondary coil, and it is the output end of the transformer. We receive output from this end of the transformer, and the voltage across this end will be secondary voltage, current will be the secondary current. And this is the soft iron core. Both the coils are wound over this soft iron core. So these are the important parts of the transformer, primary and secondary windings. A number of turns associated with the primary coil can be considered as NP, N suffix P. And similarly, the number of coils associated with the secondary coil can be considered as N suffix N, NS. Okay. Now, what is the working of a transformer? See, an input AC voltage is applied across the primary coil. As a result, alternating current is produced in the primary coil. Okay, this alternating current will give rise to alternating flux. Okay, so that means change in flux is produced in the primary coil. Okay, because the AC current always changes its magnitude with fixed intervals of time. So, with the change in magnitude of AC current, the magnetic flux associated with the primary coil changes, and whenever the magnetic flux changes, an EMF will be induced in the primary coil. Okay. So, there will be two EMFs produced in the circuit. One is self-induction and the second one is mutual induction. There will be self-induced EMF in the primary coil because the magnetic flux associated with the primary coil changes due to the current flowing through the primary coil itself. Okay, and whenever the magnetic flux associated with the primary coil changes, the magnetic flux associated with the secondary coil also changes because it is kept close to the primary coil. Okay, so that is written here. There will be self-induced EMF in the primary coil because the change in magnetic flux in the primary coil. There will be corresponding change in magnetic flux associated with the secondary coil, which will give rise to induced EMF in the secondary coil. Okay, so an EMF is induced in the secondary coil also. That means secondary coil undergoes mutual induction. Mutual induction takes place in the secondary coil. And what is the expression for induced EMF in the primary coil? See, in the primary coil, self-induction occurs, and the expression for induced EMF is EP. E suffix P means induced EMF in the primary coil is equal to minus into NP. N means number of turns of the primary coil into D phi. It is 5. Okay. DF means D phi. d phi by dt, where d phi by dt is the rate of change of magnetic flux. We had already learned this expression in our previous chapter, electromagnetic induction. and Np is the number of turns in the primary coil. And secondary coil undergoes mutual induction. And what is the expression for induced EMF in the secondary coil? ES means induced EMF associated with the secondary coil, and that is equal to minus Ns d phi by dt, where Ns is the number of turns in the secondary coil and d phi by dt is the rate of change of magnetic flux itself. Okay, so these are the expressions for induced EMF in the primary and the secondary coil. Now, assuming resistance equal to 0 in both primary and secondary coil. So, if resistance is 0, EMF will be equal to the terminal voltage itself. Okay. If resistance is 0, EMF will be equal to terminal voltage itself. Why? Because we know that terminal voltage V is equal to EMF minus IR. So if resistance is 0, then this term will be 0. Then the terminal voltage equal to the EMF E itself. Okay. So assuming resistance equal to 0 in both primary and the secondary coils, the EMF induced in the primary coil is equal to voltage across the primary coil. Okay, so the voltage across the primary coil is equal to minus Np into d phi by dt. We got this expression. Why? Because in the previous slides we learned that the induced EMF associated with the primary coil is minus Np into d phi by dt. Okay, if resistance is 0, then this EMF is equal to the voltage across the primary coil. So EP can be considered as Vp itself. So that's why the expression becomes Vp is equal to minus Np into d phi by dt. Okay. And similarly, Es is equal to Vs, isn't it? So that means the induced EMF associated with the secondary coil is equal to voltage across the secondary coil. So this equation, that means E is equal to minus Ns into d phi by dt will be equal to Vs, because Es is equal to Vs now. So we will get Vs is equal to minus Ns into d phi by dt. Now divide equation 1 by 2. So which is equation 1? This is equation 1. Vp is equal to minus Np into d phi by dt, and equation 2 is Vs is equal to minus Ns into d phi by dt. So when you divide both the equations, divide the LHS of the equation. So when you divide the LHS part, you will get Vp by Vs is equal to, when you divide the RHS part, d phi by dt will be cancelled. Then you have minus Np by minus S, that will be equal to Np by Ns. That means the ratio of primary to secondary voltage is equal to the ratio of number of turns in primary coil to secondary coil. So the ratio of the potential difference or the voltage across the coils will be equal to the ratio of the number of turns in both the coils. So Vp by Vs is equal to Np by Ns, very important relation. And from this, what is Vs? From this, Vs can be written as Vs is equal to Ns by Np into Vp. Okay. Power at the input end is same as the power at the output end. That is the peculiarity of a transformer. So input power must be equal to output power. And what is the expression for input power? It is Ip into Vp. That means the current across the primary into voltage across the primary equal to Is into Vs, current across secondary into voltage across secondary. Because we know the expression for power is V into I. And this is the power at the input end, IPVP, and this is the power at the output end, Is into Vs. Okay, so this is the working of the transformer. So once again we can just go for a quick review of the working. So if we consider this as our transformer, this will be our primary coil and this will be our secondary coil. And primary coil is connected to an AC voltage source. When the circuit is switched on, AC current flows through this primary coil. And whenever AC current flows through the primary coil, the magnetic flux associated with the primary coil changes. Whenever magnetic flux associated with the primary coil changes, magnetic flux associated with the secondary coil also changes, because it is very close to the primary coil. So an EMF is induced in the secondary coil, and due to which current starts to flow through the secondary coil. So here EMF is induced in primary coil 2. that will be the induced self-induced EMF, and the EMF induced in the secondary coil is the mutually induced EMF. Okay, and power at the input and output end will be equal, that will be same, and also the ratio of voltage across primary to secondary is equal to ratio of the number of turns associated with the primary and secondary. Okay.